tutorial from Professor Roland Kawakami. And once again, if you want to ask questions, you're very much encouraged to do so. Just raise your hands and I'll run towards you to the best of my physical capabilities. So please, Roland.
Thank you very much. Thank you for organizers to give me the opportunity to give 3 hours of tutorial lectures, of which this will be the first one. It's my first time south of the equator, and it's very nice. I enjoyed it. I walked along the waterfront this morning, and it was nice. I got rained on a little bit, but that's okay. So, actually, somebody on the bus ride over asked me, "Hey, is Graphene Spintronics dead?" And I said, "Well, where is he? Where is this dude?" Okay, he's right there. You know, and I had to think about it. You know, it's been going on for a little over 10 years. And I think on its own, you know, it's interesting, but yeah, there's been a lot of studies. I mean, of course, you could always keep pushing things out. But, you know, there's really something about spins, and not just graphene, but beyond graphene. And you think, you know, I work on other materials, not just 2D materials, but also 3-dimensional materials. And so there's the same type of questions, like, well, why do you want to do 2D? What's so good about that? Okay, and there's really, and so the answer to both of those kind of questions comes out for me in a couple of ways. You know, 2D materials, among all materials, is one of the most tunable type of materials. Okay, they're atomically thin. So you can tune them, in one way, you can tune them with electric fields, like with gates. Right? You can change the carrier density a lot more than any other type of material, just purely because it is atomically thin. Right? And my engineering friends are like, yeah, that's good. It's like you can do things on demand, right? Change the voltage, you could change the property. And that's something that's really nice about 2D materials. And the other aspect about it is they're atomically thin, and so they're all surface. So they're very surface sensitive. And yet there's still a van der Waals gap. So materials can still retain a lot of their original character, but then you can change its properties by putting it next to another 2D material. Right? And there's questions like, does the exact atomic arrangement matter? Does the angle between the two lattices matter, this twisting? Right? And I was even, you know, asking about these questions. And I think these are just really, in that case, it's not tuning properties on demand in a sense, like you don't just flip a voltage while the device is operating, you know, but by design, you know, how does the system's properties relate to its structure, and this is all at the atomic scale. And so this is also another aspect about 2D materials and heterostructures, which is unique. So even though I study other kind of materials that are not 2D materials, when I think like, well, what is it that gets me excited still about 2D materials after all this time, is this aspect of tunability, even at the atomic scale. Right? So in terms of these 3 tutorial lectures, there's going to be sort of 3 main protagonists. Okay, one is graphene. For spins, it has good spin lifetimes and spin diffusion lengths at room temperature. It's a nice material for spintronics. Second material are these transition metal dichalcogenides. Right? They bring 2 things. One thing they bring is they're heavy, they have high spin orbit coupling. So we heard a lot in Stefan's talk about spin orbit coupling. And so today's talk, it'll be a lot about spin orbit coupling that is inside graphene by itself, and also when you proximatize it with transition metal dichalcogenide. And the transition metal dichalcogenide is also in monolayer limits, direct gaps semiconductor. So they're actually really good for optics. And it turns out the optics couples to the valley degree of freedom, which can also couple to the spin degree of freedom. So it's a really nice functionality you get there. And so that's the TMDCs. And the third protagonist is magnetism, and especially these new class of materials, these 2-dimensional van der Waals magnets that you can take them down to the monolayer limit, which also makes them highly tunable. There's also 3-dimensional magnets which can interface with 2D magnets, which are quite interesting as well. Right? So on the third day, we'll talk about third lecture, we'll talk about the 2D magnets. Okay. All right. So, and I will encourage, please ask me questions anytime, like from anybody, even experts. Okay. I don't always field questions well, so this would be good practice for me to, you know, respond to your expert questions. But also, I would especially like the students who are here. Please feel free to ask questions. And some of the topics I'm going to cover, you heard in Stefan's talk, but mine is even more cartoonish, right? So we'll try to get some intuition as well. All right, so this is the outline of the talk. So there's the first topic is just, and this is all really sort of the experimental half of what Stefan was talking about, right? How do you measure spin transport and spin lifetimes and so forth? So this issue of spin relaxation. And then there's all this talk of all these different types of spin-orbit coupling. So is there a way to get in there and figure out what kind of spin-orbit coupling you have? There's a variety of ways, and one of them is actually through spin transport and spin precession measurements, which are really cool. And I'm looking around, there's Sergio's here, he is very influential in this whole thing. He's there. Yarrow, we've heard about him, he's there, okay? Oh, these are all the experts. Bart Van Wees is not here, but Marco is here. He's very closely associated. Okay. All right, so I do want to just talk about the spin transport in graphene, basic experiments. And then the last parts are all about spin-orbit coupling. One is just sort of an intuition about spin-orbit coupling and the Rashba spin-orbit coupling. And it's sort of the case study because it's the easiest one to think about, although there's a number of different types of spin-orbit coupling. And then we'll go into proximity spin-orbit. So if you have graphene and then you mate it with transition metal dichalcogenide, the idea is you want to induce spin-orbit into graphene from the neighboring layer. So this is a proximity effect. And then finally, on a computer, you can always think about, or in a calculation, you can say, here are the spin-orbit couplings inside the material. But in fact, there's experimental evidence that you can see some of those intrinsic spin-orbit effects in a very particular structure we're able to see it. Okay, so we're going to learn all about spin-orbit, even more and more about spin-orbit coupling, but there's going to be some payoffs in the latter half in terms of the experiments. Okay, are there any questions yet? Okay, let's see. Okay, and then there's some key concepts. We'll talk about pure spin currents. This is electronic spin diffusion without charge currents. So there's called a non-local measurement that has been referenced already. We'll go into detail about that. There's spin precession measurements, which are useful for determining spin lifetime. And also, it turns out to be useful for determining spin lifetime anisotropy or spin relaxation anisotropy, which Stefan talked about. I'll talk about it a lot more. There's different mechanisms. There's various types of spin-orbit coupling. One's called Rashba, one's called Valley-Zeeman. There's intrinsic and so forth. And there's mechanisms for spin relaxation, which is Elliott-Yafet and Diakonov-Perel, which was also mentioned. I will briefly mention those again as well. Yeah, so if you're a student, if you could absorb these 5 different concepts, know what each bullet means, then I've done my job. Okay, that's my goal. Okay, so let's just talk about spin transport and graphene. Okay, this is so graphene is from graphite with Scotch tape. You've seen this. You have a single sheet; it becomes relativistic-like, and the Fermi level is tunable. So I think you've seen that. Wow. Is that okay, we will not worry. Okay, so, all right. I don't know what they're saying. That's okay. So the motivation for graphene for spintronics was it has low intrinsic spin-orbit coupling, weak hyperfine coupling that does not have much nuclear spin, and it has high mobility. So you put all these together, and you have possibility for long spin lifetimes and long spin diffusion lengths. And theoretically, it should be like a microsecond. I think the best is tens of nanoseconds or so. So it's still far short. And then the spin diffusion length, it can be longer, but it's been pretty long. It's the longest of any material. So I would say this is quite good. It's quite good. And the birth of the field is really from Bart Van Wees and his group. Here is a piece of graphene monolayer with cobalt electrodes. And then, there'll be a few slides to explain all this stuff, but you basically, have a current source connected and you inject some spins on one side, and then you have a voltage source on the other, a voltage meter on the other side, and then you detect them. So you're actually seeing spins go from 0.3 to 0.2. Okay? And then this is what a spin transport signal looks like. And then this is what a spin precession signal looks like. So if you apply a magnetic field that's perpendicular to the spins, they're going to start precessing, and then you get curves that look like this. Right. So I'm going to go over each of these in some detail. Okay. So this is what a non-local spin valve looks like, a lateral spin valve. There's some cobalt electrodes for injecting and detecting, and then there's 2 additional electrodes that are for reference. I'll explain that. And then there's a silicon dioxide dielectric layer, and the silicon substrate is conducting, and that's a backgate. All right, so we can use this to change the carrier density inside the graphene. And here is a picture. I used to show the same picture of the device for like many years. This is a new picture. So I like this picture because I made it myself. The other stuff was done by students. I did this myself, so I'm very proud. It's multi-layer graphene. These are cobalt electrodes and some gold. The fat ones are gold. So you have a lot of cobalt electrodes because they're not all going to work, so you just go through all pairs possible and then hopefully you get a signal. Okay. This is how the measurement works. You take on one side of the ferromagnet, it's a spin injector, and you put a current source, and then you jam some current through, and this will generate a spin polarization inside the graphene underneath this electrode. And this is called non-local because what happens is we have a charged current, and so to the left, let me push this. Oh, to the left is a spin current. It's actually a spin polarized charged current. Okay? But to the right is what's a pure spin current where you have spin diffusion. So it's electron spins and they're diffusing to the right, but there's no net charge current flowing to the right. So it's just the spin current. And the way that you can think about it is imagine if you had spin up electrons going to the right and spin down electrons going to the left. The net charge current is going to cancel off, right? But then you have this sense of a net flow of a spin, right? So this is actually a very nice way to do the measurements. It gets rid of a lot of artifacts and lots of background. And then what you do is for the detector, you just measure voltage between ferromagnetic electrode, which is the spin sensitive, and then like a gold electrode, which is not spin sensitive, right? And this voltage will correspond to the spin density that you get there. Okay? And even taking a step back further, when you do the spin injection, you apply a voltage, and this is your current. And this is our injection. We're taking electrons from the ferromagnet, and the ferromagnet has a spin-dependent density of state, so you have more spin up than spin down. And so you're going to jam that across, and so you're going to start populating the spin up side of the graphene a lot more than the spin down. And this should actually look like a Dirac cone, but I never changed it from a previous talk. So we start getting it in balance. And the nice thing about spintronics is you have a different chemical potential for spin up and spin down. It's like instead of just mu, you have mu up and mu down. So you have like 2 channels. So more information that you can have in there. Okay? And so this is actually a voltage difference. And that's why you're able to detect the spin density as a voltage. Okay? And you could understand it here. So if I have a spin injector here, I have the spin splitting, spin up and spin down. And then as it goes to the right, it decays because you have some spin flips. So you have some spin relaxation. And the detector, it's a voltage measurement, and if it's a perfect spin detector, I would measure, if the magnetization is pointing up, I'll be measuring the mu up. If the magnetization is pointing down, I'll measure mu down, the chemical potential for down. And as long as you have a spin density, you have a different mu up and a mu down. The parallel configuration and the anti-parallel configuration will give you a different signal. So here it's positive, and to the left is positive, on the right is negative. And now this point confuses some folks. It's just common in the literature to take this voltage difference, which is the spin signal, and then to normalize it by the current and call that a non-local magnetoresistance. So it's not a resistance in in a regular sense. It's just a voltage signal that's normalized out with the current. Okay? So this can be a negative number or a positive number. Okay, it's all fine. Yes, question, microphone. Yeah. Yes.
So can you comment for the benefit of the students and the
Yes.
non-experts about the timescales for the relaxation, so you can establish a chemical potential and actually use this description?
Okay, that's a good question. What's the time scales? So typically this is viewed as a DC measurement, so you're flowing in a DC current, and so this profile is steady state. Okay, so that's one thing. In terms of the spin lifetime, typically it's on the order of 100 picoseconds, a nanosecond, 10 nanoseconds, right? So this is sort of all just steady state. There's no dynamics. And in an actual experiment, you might use a lock-in amplifier, and you might actually have this current go positive and negative at a frequency of like 12 hertz or 13 hertz or something like that. But that's basically DC compared to, 10 nanoseconds. Okay, yes.
But they have a local equilibrium where you can define a chemical potential. What is the time scale that you need for that?
Oh, the local equilibrium.
Well, you have to define a chemical potential, right?
Oh.
That's position dependent.
Yeah, so that's a good question. What time scale is that? I mean, I would say that that's probably like a thermalization time, which is relatively short. I don't know what the latest is in graphene on that. Right. So I think if you can get back to like a Fermi-Dirac distribution, like after, because some of these are tunneling injectors, so there'll be hot electrons inside the system. I think in graphene that can tend to be longer than in other materials, but I would guess on the order of like the picosecond type of time scales. So, okay.
Energy relaxation, right? You inject on top of, like when you do femtosecond type spectroscopy, you have to wait until things, relax, and you can define a chemical potential.
Yeah.
But this is phonons, it has to be phonons, some kind of electron-phonon interaction. Or electron-electron interaction, even
for the thermalization, probably. I mean, Sergio back there is an expert on this. He has a nice paper. Or where's Juan? Yeah. Do you have a comment on thermalization timescales?
So electron-electron interaction is in the order of picoseconds. So it's extremely fast compared to all of these time scales. And you will see in my talk about the thermalization and all this stuff.
Yeah, good. So there's a really important experiment, for this whole talk about precession. I'm sorry. So basically here, this is like experimental data. You apply a field along the long axis of the electrodes, and then you just ramp it, and the point is to get parallel and anti-parallel orientation. So when it's parallel, you'll end up with essentially like a positive voltage, and then when one of the electrodes flips magnetically, then you get anti-parallel, and you'll have a different value. So this, I've subtracted off some background, so typically there's some background that's not related to spin. So you always look for this switching between parallel and anti-parallel. And so that's your spin signal. And then you can analyze that to figure out, how polarized your spins are. Okay. This is the spin precession turns out to be a very important experiment. I mean, historically, when people saw these type of signals, the question would be, well, is it really a spin signal or some stray field or other artifact? What's going on? And it was the fact that people had observed spin precession, or these kind of curves. Well, the kind of curves I'll show you, spin precession effects. I said, oh yeah, this is really from spin. It's not an artifact. But it's even more important than that. It's a way that we're able to look at spin-orbit coupling, spin relaxation, even magnetic proximity effects, and so forth. So I wanted to go and see what should this signal look like, right? I have spins being injected. I apply an out-of-plane field, and therefore they will precess, and then they'll end up at the detector. And what will the spin signal versus the applied field out of plane look like? Is it a damped cosine? So that's what you might expect, because there's a really well-known experiment on silicon by Ian Applebaum. And so they basically are injecting some spins into silicon, and they go like long distance, and then they detect it with some special type of detector. And if you apply a magnetic field, say in this direction, that's perpendicular to the spins, then they'll start precessing. All right? And then you can sort of see that as you apply a larger field, they'll precess faster. Right? So then the more precession you get, the more you'll see that as oscillations at the detector. So you can sort of see this, right? So this is a spin precession as a function of applied field, right? And the reason why you see this is because you put in a large voltage across the injector and the detector, and so the electrons will be like this kind of packet, and they'll go from here to here to here. So it's a spin precession under the spin drift, they call it, because you're pushing the electrons through. But that's actually not what we have in our case, right? So those who are knowledgeable about such experiments will be like, Okay, well here's our data, and you sort of see, it looks like it's precessing, but you only get like one oscillation and then it sort of dies out. And so people who are really familiar with this experiment will be like, where's your oscillations? That's not precession, where's your oscillations? But it's actually a real different kind of situation because, between the injector and detector, we're not applying a electric field. So we inject some polarization and then they diffuse. So the packet is just spreading out, right? So the amount of time it takes for a given electron to go from injector to detector is going to be very different because it's like random walking diffusion of these electrons, right? So instead, what you end up getting is the spin precession actually creates dephasing, right? So, you see one oscillation, but by the time you get out here, you have no more oscillations, right? But this black curve is the theoretical expected shape for spin precession, right? And what's important about this? One thing that's important is you could extract out the spin lifetime. The narrower you get, the longer the lifetime is. So this is about 771 picoseconds. It's not that accurate, okay? Let me go further. And the type of expression that you would basically say, well, I'm going across the channel. There's some diffusion properties. So this is like the solution to diffusion equation. You have some precession, that's the Larmor precession frequency. And then you have some decay, which has the spin lifetime in it. So you put all those two together and you get curves like such. And this is an earlier device that had much lower spin lifetime. It's like less than 100 picoseconds. And you can even get the diffusion constant out of such fits. Right, so this is like a very important measurement to get spin lifetimes. Okay. Now there is this kind of technical detail which is historically very important, and I'll tell you about this. Oh yeah. What does the charge mean free path? I don't know. These are not high mobility. So I'll give you, I don't know.
It's in the diffusion constant.
The diffusion constant is like 0.02, or typically in these on SiO2, and it goes like 1 order of magnitude higher for on HBN. Yeah, so typically it's like this amount. So if you could translate that into mean free path, that's it, right? Yeah, there's this work by Christoph Stamfer. They put it on WSC2, so they can get much longer distances. So like Stefan was mentioning that. So I think that's a really interesting regime to be in. So these are just more garden variety, low mobility stuff. Thank you. Okay. So there was this. I think I will go through this somewhat. But there's this very famous issue of conductance mismatch for spin injection. And there's some expressions here, and I won't get so much into the expression. But there's this concept of spin resistance, which is similar to resistance where you have resistivity and some length over the area. But instead of using length of the resistor device, it's actually the spin diffusion length, okay? But the most important thing is the direction of flow that a spin wants to go. It's really connected to the resistivity of the material. So basically materials that are less resistive, so more metallic, then the spins like to flow in those directions. That's just how the spin diffusion works, right? So when you start trying to inject spins into graphene, say with cobalt, the problem is that you can inject nicely with a voltage, but what happens is that the spin resistance is so much lower in the cobalt because it's metallic, more conductive, that you get lots of backflow, okay? And so the solution to that was proposed by a number of folks, including in the original paper on conductance mismatch, and this was for semiconductor systems. And then if you put in a tunnel barrier, what you can do is you can use the bias to inject across the barrier, but then in terms of the spin flow, you won't get a backflow back into the cobalt because you have a highly resistive tunnel barrier. And in fact, you can keep a lot of the spin polarization, the spin density inside the graphene. So this turns out to be really important just to have better performing devices. But it also turns out, which was more surprising, that if you start looking at the lifetimes as you put on transparent or put on some pinhole contacts, or even you get tunneling contacts, you start noticing that when you start fitting these Handley curves, your lifetime gets longer and longer. And yeah, and then so in the early days, you can only get like 100 picoseconds or so, but then you can start getting close to nanoseconds if you get good tunneling contacts. And the idea is that these contacts are much less invasive, and they can give you longer lifetimes. And if you looked at it even closer, you can think about it in a slightly different way. You have the Handley curve, which has a diffusion process, the precession, like I mentioned here, and the relaxation. But it only, there's actually two ways that you could lose spins from your system. So one of them is if you have a spin flip. So if you imagine you have this isolated graphene and it's going to have spin flip, like some type of relaxation process, that's fine. But in a real system, in a device, you actually have a process of the spins getting absorbed into your metal or your ferromagnet or non-magnetic detectors. So even though they didn't spin flip, which is sort of like what we feel is like our intrinsic to graphene properties, the contact itself can make the apparent lifetime look a lot shorter. So there's the loss due to relaxation and there's the loss due to absorption. And so this is an effective spin lifetime. And at least in these kind of expressions, they don't take that into account. And I'll just mention that there have been more detailed models, initially proposed by Van Wees, and then by a couple of other groups. There's analytical models. They look a lot different, they look a lot scarier, but they fit just as well, and they take into account all of these absorption effects. Right? So the moral of the story is if you want to have good spin lifetime measurements, you got to have good tunnel barriers to block, with high enough resistance to block the spin absorption. And then you'll be fine using the standard Handley type of equations. Okay, so this is a little bit technical for practitioners, I would say, but it's sort of mysterious. Like when you measure a spin lifetime, what's going into it? Is it from spin-orbit coupling? Is it from this Dyakonov-Perel? Or is it just your contacts are bad and that's limiting, your ability to measure anything intrinsic, right? So in the early days, the devices were just bad. Now the devices are really good, so you can get to the point of measuring these intrinsic spin-orbit type of effects. Yes, question.
So the conductivity mismatch is essentially the same as you had for semiconductors. You also need a barrier here.
Yes.
To overcome the conductivity mismatch.
Yep.
Spin filtering is what you get.
Exactly.
Okay.
Yep. Yeah, but actually all the knowledge from the semiconductor work was like, well, we know that this is going to be the deal for getting higher signals. But the part was not clear was the whole business with lifetime. We didn't know that it would affect lifetime. Because there's so many things going into the lifetime, you don't know what's the worst thing there. They're all bad, but what's the worst? And initially it was the electrodes. Okay, so what's happened? What's happened is there are these early studies on SaO2, good tunnel barriers developed, which made the lifetimes longer, spin diffusion lengths longer, and then heterostructures got utilized like HBN, and now in the tens of nanoseconds, 30 microns spin diffusion length. So there's been a general progress in terms of quality of the material and the spin properties. Okay, and here's some of the data. This is from Van Wees's group.
Maybe a quick question before you move on. Just
yes.
I forgot to ask. Does that depend? Because essentially the injector is the graphene. In one of your slides, you had that, right? That's the ferromagnetic layer, so to speak. In one of the slides, you had the sketch where you're injecting from the graphene into MgO or something.
Oh yeah. So like this picture here.
Yeah.
So the injector here is cobalt.
Yeah.
Yeah, and then there's MgO, and then it goes into the graphene.
So does that depend really where you are in density in graphene, where the chemical potential lies?
Yeah.
The conductivity mismatch, does it depend on this?
Yes. Does it depend on the density? It does. Yeah. And there is
Can I invert it? Can I?
Yeah, there's a typical. I have to refresh my memory, but there is a typical gate dependence of the magnitude of the signal. And I think that could primarily be understood in terms of this conductivity mismatch. Like if you have more carriers, the conductance is higher, so that goes into the conductance mismatch.
Then in this case, you could reduce the barrier, or you would not really have a conductivity mismatch. And have people looked into this in this regime?
I think that's a very challenging thing to do. I'm not aware of too many really systematic studies. I think Bejotin has done it the most. I think he's done it the most in terms of how you change the barrier, contact resistances, and how does that affect the signal. But, you know, I think, what do I think about it? I think it's an important question. We're kind of interested in these questions related to van der Waal barrier, van der Waal gaps, 2D magnets as well. So that has not been explored at all yet. I mean, those might actually be enough. Okay, those might be enough to be good. Yeah. Okay, thank you very much. Oh yeah, so here's just the high quality. We've seen this earlier. Okay. Long drift lengths, relatively long spin lifetimes. These are the best. Okay. So I'm looking at the time, and I'm not going to worry about it too much because if I don't get to certain things, I'll just do it the next. Please ask questions. Do not worry about that. So I did want to talk about spin-orbit coupling in a slightly more cartoonish fashion than Stefan has done, but it's very similar. So you know, if you think, you know, I have a charge. It's a spin-orbit coupling is a relativistic effect, right? If I have my electron is moving past the charge like a nucleus. This is what it looks like. Let's say I have a velocity v and a momentum in the lab frame of k, pointing up. But if we switch over into the electron's frame, which we'll call S prime, so this is S prime, then what it looks like is that the electron's at rest, but the velocity, this particle's moving with the velocity down here, and then this has a slightly different electric field, but you know, with Biot-Savart law, you will create a magnetic field B prime, okay? And so this magnetic field that's experienced by the electron, that's called the spin-orbit field, B effective, okay? And the direction it points in is just E cross V. So if you just do E cross B, E cross V, or E cross K, it points along the magnetic field direction. So this is like a spin-orbit field that is experienced by the electron, okay? But this is just for like a single nucleus, a single atom. If you want to think about it in terms of a solid, it turns out if you have a solid that has inversion symmetry, all of those electric fields will cancel and you get nothing, right? So but if you have systems that break the bulk inversion symmetry like gallium arsenide, so this was done by Dresselhaus, so it's called Dresselhaus spin-orbit coupling, or monolayer MOS2, these TMDs, they break inversion symmetry, so you can get a spin-orbit coupling from that. Or you could have structural inversion, so this is the Rashba. And so if you have an interface that breaks the translation symmetry, or if you had an electric field that breaks the mirror symmetry, I should say, or if you have surface impurity. So these can all create a type of spin-orbit coupling due to structural inversion breakings called Rashba, okay? And I want to just sort of talk about things in terms of Rashba because I could have cartoon pictures and intuition about it, but the other one is also very, very nice. So if you open up your textbook in electricity and magnetism, you have, you know, the Lorentz transformations from the lab frame, E and B without the primes, to the electron's rest frame, which has the primes. And you notice that certain components of the electric and magnetic field, you know, mix, like here. So this in the electron's frame, this is the extra field, and this is basically the E cross K we had the previous slide, and that's the B effective. So the idea is like if I have an electric field that's vertical, it could be a real electric field, or it could just be a potential gradient from an interface. It doesn't have to be a real electric field. And then if my electron is moving past it along this red arrow direction, it's going to experience an E cross K effective magnetic field, and that's the spin-orbit field. And so that's in systems that have various inversion symmetry breakings. Okay? All right, so now we saw in Stefan's talk as well, we know that the interaction of spin with a magnetic field is S dot B with a minus sign. And then this B effective is E cross K. And then you just do some vector math, you permute it, and then you write it out because the momentum is in X and Y. And so here, this is the actual electric field, but to be a little bit more general, if it's from a confining potential or some interface potential gradient, we could just put it in terms of a general coefficient, Rashba coefficient. So it's basically a coupling between the momentum in the XY plane of your electron and then the real spin. So this is the Rashba spin-orbit coupling. And so we can actually solve this in the next couple of slides, and this is your solution, spin momentum coupled states, which Stefan showed, so I will go past it. And here is the actual solution. You have the momentum squared over 2m, and then you have this Rashba spin-orbit coupling term where these are these Pauli matrices, sigma x and sigma y, or sx and sy. And then so it becomes a matrix, 2 by 2 matrix here that you just multiply out. Schrodinger equation is this matrix, H times the wave function is equal to the energy times the unit matrix. Okay, so you do all this stuff, and you get for the solution the eigen values for the energy look like this. You have the momentum, and then you have this kind of 2 bands which are spin split. Okay, and so there could be a homework problem, but you just basically diagonalize the matrix, and you end up getting over here 2 branches. One where the spins, if you calculate the eigenfunctions, you find out that they're in plane, and they rotate, they circulate one way for one of the bands and then the opposite way for the other band, right? So, okay, so we did all this stuff. This is the Rashba. And this is not even for graphene. This is for a parabolic, massive particle, okay? And the thing that I really want to point out is that it creates an effective spin-orbit field that depends on the momentum, and it's also in the xy plane. It does not point along z, it points along x and y. So this is sort of the character of Rashba spin-orbit coupling. Okay. So let me pause there. Are there any questions? This is from students or anybody? It's good? Okay. So I do want to tell you about what happens in graphene. It's similar but different, okay? Here is the band structure of graphene. It's Fermi velocity h bar times sigma dot k. Sigma is the lattice pseudospin, which describes how much wave function is on lattice A and how much wave function is on lattice B. Okay, and so Stefan talked about that. And so you have the Rashba Hamiltonian looks more like this, which has real spin. It has this lattice pseudospin. It's dotted with the z direction, which is like the electric field, or the symmetry breaking is along the z direction. And then if you solve it, it's very similar, but what you end up is, because you have a 4 by 4 matrix instead of a 2 by 2 matrix, you end up with 4 bands. And so there's these conduction bands, and there's the valence bands. They get split into 2, it's spin split, and the orientation of the spin is in plane and they circulate. So there's a lot of similarities between what you get in graphene as what you get in like a regular 2-dimensional electron gas, but you just have an extra branch for the holes. So you have electrons here and holes down there. Okay, conduction and valence bands. But this thing that's really similar about it is that you have a spin orbit field which is in your xy plane. So it's in plane. And there's other kinds. So, yeah. And so there's this business about once you have spin-orbit coupling, how does that destroy your spins? And Stefan did a great job on this. One is Elliott-Yafet. Whenever you have a collision, you have a chance to spin flip, because when you have spin-orbit coupling, your spin up and spin down are not your eigenstates. It's spin up with a little mixture of spin down, and spin down with a little mixture of spin up. So when you scatter off of an impurity or a phonon, you'll get a non-zero chance for a spin flip. So the more scatterings you get, the more spin flips you get. And we all stole these pictures from Yaro's website. Okay, thank you. All right. And then the Dyakonov-Perel, which Stefan talked about, is really driven by precession about these effective spin orbit fields. Okay, so a lot of the next discussion is going to be really about these kind of effective spin orbit fields. Okay, so I will not go much more into this. But there's this way to think about this Rashba. And if you look here, the out-of-plane lifetime and the in-plane spin lifetime. So let's imagine we have this kind of effective magnetic field and that circulates like such, right? If your spin is out of plane, then this field will cause it to precess because it's perpendicular. This field will cause it to precess because it's perpendicular. So everywhere around here, it's going to cause it to precess, and it's going to destroy your spins like such. But if your spin were in plane, it turns out like this one, the horizontal effective field is perpendicular, so it will cause it to precess and dephase. But the ones that are parallel, if the effective field is parallel to your spin, it's not going to precess. So for in-plane spins, the effective field can only have half as much ability to precess the spins, because one of the directions is parallel and only one of them is perpendicular. Whereas this one, they're both perpendicular, right? So that therefore, the lifetime for spins in plane is going to be double the spins out of plane, right? Because this one can get killed twice, This one can only get killed one way. This is two ways. So the in-plane can live twice as long. So this is the spin relaxation anisotropy for Dyakonov-Perel spin relaxation, okay? And so it really comes down to, if you can really determine what's the lifetime for out-of-plane spins compared to the lifetime for in-plane spins, if it's anything different from one, you got a really big clue of what's happening inside your system. Right? If it's one, it could be almost anything. But if it's like bigger than one, then it's something. If it's less than one, it'll be this stuff, okay? So the remainder of the talk will be looking at different situations where we have this spin lifetime anisotropy. Okay, so there's going to be sort of 4 situations. So one thing is to use this kind of technique to look at proximity spin-orbit interaction. So let's imagine we put some transition metals like chalcogenide on top of graphene. What kind of spin-orbit interaction do you have inside this heterostructure system? And then the other one we'll look at is spin-orbit effects in gated bilayer graphene. Okay. Right, so here's graphene. Here's the transition metal dichalcogenide. It has this type of structure. And here's the heterostructure of the two. We know about graphene. In terms of the TMDC, it has a really strong spin-orbit coupling. There should be an OR there. And it also has some nice optical properties, which I won't talk about today. Okay, but the nice signature about the band structure of, say, MOS2 is that if you look at it, it has these kind of bands, conduction band and valence band, and they both have some spin splittings, but they're especially large in the valence band. Right? They could be hundreds of MeV. And if you're in the, say, K valley, then you have a spin up and spin down. If you're in the K prime valley, it's opposite. So it's like this spin valley coupled band structure. And the important thing I want to point out is the direction of the spin is not in plane like all this Rashba stuff. It's out of plane. And it's a different, and it has a name like Zeeman. It's like if you applied a magnetic field along the out of plane direction, you get a spin splitting, and your quantization axis will be out of plane. Right? And then they call it valley Zeeman because it's opposite in the opposite valleys. So this is the K valley and momentum space and the K prime valley. Right? So they're spin valley coupled because the opposite valleys have opposite spin splittings. Okay? This is very different from the Rashba. Okay, so now Yarrow did this very nice calculation, and there's a whole lot of stuff here, and I can only claim to be 90% accurate of what I'll say here, but he's here. If you have a real hard question, we'll get there. So there's a lot of things that happen when you put the TMDC on top of graphene. So one thing that the TMDC does, and I'll just note that if you look at it from the top, it looks like a honeycomb lattice, very similar to graphene. Okay? And so, but the A lattice and the B sublattice are not the same. So one thing that happens was when you put it on graphene, it's going to break the AB sublattice symmetry, right? And it's actually because they're both carbon, that's why you get a Dirac point. It's enforced by symmetry. So if you break the AB lattice symmetry, you're going to open up a gap. So that's one thing you have here. You open up a gap because the TMDC is going to break that symmetry. And it turns out there's 3 types of spin-orbit coupling. One that looks like this, which is like the valley Zeeman. Another which looks like this, which is the Rashba. And there's a third one, which is pseudo-spin inversion asymmetry, which if it's buckled a little bit, okay? And then I don't know the name of that, okay? And the thing is, the direction of the spin-orbit field is different in all cases. So for the valley Zeeman, like what you have in MOS2, the spin-orbit field is out of plane. It's along Z, plus or minus Z. The Rashba is along XY. It's in plane. And so the Rashba, the ratio of out-of-plane spin lifetime to in-plane spin lifetime is 1/2, right? Whereas for valley Zeeman, it's actually, since your spin is out of plane, since your effective field is out of plane, if your spin is out of plane, it's very happy. It'll live a long time. But if it's perpendicular, then it's going to precess like crazy and dephase very fast, right? So this ratio is going to essentially go to infinity. It's going to be very large, right? Because the spin in plane is very small, and the spin for out of plane, lifetime for spin out of plane is very large. So, if you do an experiment that could measure the spin lifetime anisotropy, then you can really tell, if you're lucky, that you have one of these two because they're so far different from one. Okay, and here's a table. Here's the pictures of the band structures you get, and here's a table of all the values. So this is very nice, right? And it seems like this valley Zeeman type of term is typically a lot stronger than the Rashba. Okay. So let me pause. Actually, this has got that was a little tiny theory section. Are there any?
I have questions.
Yes.
Can you go back to the table?
Yeah.
Can you tell us a little bit how these numbers are extracted? from experiment, or is it?
Oh, these are all calculations.
Maybe you should ask the theorist then later.
Martin did this. He's right here.
No, he's giving a talk there.
Yeah. Okay. So how do you get it? So the first studies were actually charge transport measurements, like weak localization, because there's these HLN models. There's various models, and if you have spin-orbit coupling, it's going to make your weak localization peaks. It could flip over and things like that. So that's fine. Those are legit. But I like this spin transport experiments. So there's a way to create spin transport experiments, and the first was introduced by Sergio in this Nature Communications article in 2016. And then, this and related methods were used to actually measure to measure anisotropy of the spin lifetime. So values that differ from 1. Okay. So this is the idea. It's a great idea. The result was a null result, Sergio. But it's okay. But it's a very important null result because there were some reports that there is spin lifetime anisotropy in monolayer graphene. And this work showed that it was wrong. The previous result was not quite right. Okay? So the idea is when we do Handley, we apply out-of-plane field, and then the spins will precess in plane, and the entire time they stay in plane. So the lifetime you measure has to do with the lifetime of in-plane spins, and that's it. But if you tilt it, now the precession is going to go into a cone. So sometimes it's in plane, sometimes it's out of plane. So when you do sort of the curve fits, you extract out information of out-of-plane lifetime versus in-plane lifetime if you do this not just for one angle, but you do this for several angles, right? Then you can figure out what's the lifetime of spins when they're out of plane and what's the lifetime of spins when they're in plane, okay? So I thought, wow, this is very clever. And, there's regular Handley curves. This is this curve here where it's out of plane, 90 degrees. So that's out of plane. And then trying it at all different tilt angles, and you get these nice curves. And these curves are defined by some very difficult equation. But it turns out the saturated value is described by a simple equation. And then if you do this experiment, saturated value, and then you do, these 4 curves are for 4 different carrier densities, so we can just focus on one. So we start with in plane, which is at 0. This is the saturated value, and then you can go all the way to out of plane. And you trace out a curve. So this curve is like this value out here, the saturated spin signal, okay? And then you just replot it, and this is as a function of the tilt angle, and you replot it as a function of cosine squared of that angle with the star, which we won't worry about. And all these lie on this diagonal. So this is the signal size, and this is the cosine squared of the angle, and it falls on this line. And the importance of that is if you're above the line, your anisotropy ratio is bigger than 1. If you're below the line, this anisotropy ratio is less than 1. And if you go either above or below, then you've learned a lot about your system. It's like beautiful. And of course, the result that came out was it's on the line, which means 1.0, means there's no spin lifetime anisotropy, and therefore we've learned almost nothing. Well, what's that? I'm baiting him to talk. What did we learn from this?
Well, we were looking for information to know what the spin relaxation was coming from. So what was the origin? So if it was anisotropic, then it was dominated by the spin-orbit interaction. And if it is isotropic, it should be something else. And so, these would indicate probably that it could be magnetic impurities that are paramagnetic. It could be something that does not have a preferential direction. So that was the indication of this paper. But you knew
correct,
that,
yes.
so you really
made
me talk.
It could be magnetic impurities. It could be Elliott-Yafet. It could be other such things. But yeah, it didn't really. Yes, so it definitely had a lot of value.
Roland, do you know when it was done about 20 years ago in 3.5 semiconductors? Did oblique Handley show any anisotropy?
Oh, I don't know. That's a good question.
Do you know, Sergio, in 3.5s? there were junctions. I think it was like spin LED junctions. Safarov did it. So maybe it's good to check whether there is something already in simple semiconductors about this anisotropy.
Yeah, maybe. But that's like there's like a more bulk system. So I don't know if in-plane or out-of-plane intrinsically has a big difference, right? So, I mean, if you were doing out-of-plane and in-plane, you might learn about induced Rashba kind of effects. So I think it can tell you a lot. I don't know if it's been studied, though, that way. Yeah. Okay. Okay. Yes. Yes. So I will say, actually, there was another report soon after at lower temperatures out of Regensburg where they did see some onset of spin relaxation anisotropy and monolayer graphene, and in a different parameter space than what you had. And we also saw that, but never wrote up the paper, so that happens. But yes.
So I'm just trying to put it in perspective again. When you showed your slide with the infinite lifetime ratio and then the half for the two. Yeah. So you learn it's not infinity. Right? Yeah. So that's one thing. Whether it's whatever, we don't know. That's what you mean by not learning.
Yeah. So we did learn that it's not like some Valley-Zeeman or intrinsic type of effect dominating. We learned that it was not a Rashba effect like dominating. And then, but it could be a list of a variety of. So it eliminated a couple of options. So that was very important there. And there were some previous reports that this thing does exist, and this really showed that it's like one and so forth. So I think that's good. But I said, wow, this is so beautiful. But when can this be useful? And of course, Sergio and Bart had really great insight on the following. So this is the next slide. So, what if you were looking for, it's intrinsic spin orbit in a sense, like it's not from random stuff going on. And you take a TMDC, in this case it's WS2, and you put that on top of your graphene, right? And in principle, that will induce a spin orbit coupling. According to Yarrow's calculations, it should be this type or that type. And doing the exact same kind of measurements, a spin valve with TMDC with WS2, doing this oblique Handley, and you have these kind of curves going in all these different directions. And what you do here is you take the saturated value again, and these are all different angles, and then you plot them as a function of like cosine of that angle, essentially. So here's your spin signal. And so this is the curve which was not anisotropic, so this is just the graphene. This is the TMDC on top of graphene, and it is completely different. This is completely different. When I saw these papers come out, I was like, this is like really, really smart. It's much, much larger than 1. Like, see, if you look here, if it's above the curve, it's bigger than 1. It's like 1.8, 1.5. But this is like so far over. It's not just expanding out. It's like huge, right? So this spin lifetime anisotropy is much, much bigger than 1. So it means that it's consistent with the proximity spin orbit field that's out of plane. So this Valley-Zeeman type of coupling is dominating the system. And so it's similar to what you have in the TMDC. And so this is like, this and is another work that came out. They're both around the same time. They're both beautiful. This is another way to do this. And this was also in Sergio's paper as well. But the other way that you can do this, not just tilting, but if you, in fact, took a magnetic field and applied it in plane instead of out of plane, and you inject a spin coming this way, it's going to precess and come out of, it's going to point out of plane. And if it turns out that the out of plane, the relaxation is the spin lifetime is much longer when it's pointing out of plane, then when it rotates out of plane, then they're able to get to the finish line, the detector, like much more, with much more spin polarization, right? So you can do this in-plane field, Handley spin precession, so it rotates out of plane. And when you do that, normally you would just see a peak and it would decay. And that little thing is, you could barely see it. What happens is that when you start processing it, then, when you rotate, when it precesses, the signal becomes gigantic. It increases like tenfold, right? So when you're in plane, that's the unfavored direction for a Zeeman type of spin-orbit coupling, Valley Zeeman. So it gets killed. And it's when you rotate them out of plane, they can make it to the end. And that's these huge lobes on the side. Okay? So here, they're estimating that the out-of-plane spin lifetime is 40 picoseconds, whereas the in-plane spin lifetime is like 3 picoseconds. So there's this huge anisotropy, and this result is also consistent with this oblique Handley result. It's just showing that out-of-plane spin lifetime is much bigger than in-plane spin lifetime. Okay. And there's further studies on these same systems where you look at, injecting and detecting without the TMD, it looks normal. So this is the peak, the Handley peak. The outside part is when you apply enough field that causes the magnetizations to point along the field. So ignore that outside part. So here you have a nice signal, normal Handley curve. If you put the TMDC inside there, all that spin transport is blocked. Okay? Over here, if you do an in-plane field Handley, it's pretty similar. So if you look at this curve compared to this curve on the left, there's a peak of the blue here, and there's a negative peak for the red, and they look kind of similar. Okay? But then when you compare it here, when you put the TMDC in here, right? When it was out of plane, it was completely blocked. But now they can rotate out of plane. They actually get enhanced, right? So this is really showing that the out of plane spin lifetime is much, much larger than the in-plane spin lifetime. Okay, so both of these styles are showing that you have graphene, and by putting a heavy high spin orbit coupled system like the TMDC on top of it, that you can induce the spin orbit coupling into the graphene. So this is the proximity spin orbit interaction. So I think this is like beautiful, beautiful work.
Sorry, can I just make sure I understand this? So the infinite you had before was the other way around? It's perpendicular to parallel? No, this one, the one here, out of plane, yeah.
This one?
Yeah, no, the second one.
This one. Yeah, so in this one, the spins always stay in plane. So therefore, the lifetime is always short. And so it just doesn't get to the finish line. So that's why this middle part has no peaks. Yeah. And this one, it makes it, but you get a big peak here because it's when you reach 90 degrees of precession when it hits the TMD, and then so that's why you get a big peak out here. Yeah. So what I'm going to do is, I had one last section, but I'm only going to show this last slide. And so what's next? So I think this is a really great idea from Yarrow. Okay, so leave a few moments for more questions. He said, well, you know what? Would it be so great if you can use this kind of proximity effect and control it electrically? And the idea is if you had bilayer graphene, what you can do is you can apply a gate and an electric field. So if you apply a certain electric field here, then the carriers will all be in the close layer, the proximal layer, and they will feel the effects of the TMDC. So this one has a high spin orbit coupling, and then your spins will not make it across so easily. So this will be like the spin orbit coupling's on, the transistor sort of in the off state. On the other hand, if you reverse the electric field, now your carriers will be in the remote layer, the far layer, okay? And they don't feel the effects of the TMDC as much because it's further away. And then so there's much less spin orbit coupling. So the spin orbit coupling is off, which means the spin signal is on. So this is a very, very nice idea. As far as I know, it hasn't been realized yet, but it's a very, very nice one. Okay? And so there actually is a fourth topic, which is work that my group has done, and I'm going to not go into it, just for sake of time. Okay? I might go into it at the start of the next lecture because I kind of like it. But so I'll just pause. Is there any questions? I could take a few more questions. Yeah.
Well, thank you, Roland. Any more questions?
So concerning this isotropic relaxation time, so does this tells me something about the spin